Okay, you're going to need the properties of metallic, ionic, and covalent. Now, my friends in chemistry, we have some words that might be changing up on you a little bit. You need to understand from last night that ionic compounds, metal, non-metal, or anything positive, anything negative attracting, it could be a metal and a polyatomic ion, or it could be a polyatomic ion like ammonium and another polyatomic ion. I gave you all the combinations between ions, is called ionic. No big deal. What if I give you something that has metallic bonds? We call that a what kind of bond? Metallic bond. Whoa! We have metal, non-metal normally. We know there's others examples of ionic bonds from what the heck is that table. But metal, non-metal is ionic. What's that?
On your
I'm not sure.
video.
What? Yes, exactly. We'll get to that. So listen for a second. Ionic. Normally, metal, non-metal. That gives you a transfer because the difference in electronegativity. Then we have what we've been studying for a while. Covalent compounds. Non-metal, non-metal. Between the sulfur and the oxygen and sulfate is what we call covalent bonds. They're forced to share because the difference in electronegativity is high. So we've got metal and non-metal, ionic. We have non-metal, non-metal, covalent. Sometimes they're sharing equally, sometimes they're not. Sometimes I feel like a nut. I'm sorry. Yes. Yes, you can. What's the last combination? Metal, non-metal. Non-metal, non-metal. What's the last combination? Metal, metal. That's called metallic. Now, how can I explain metallic bonding? It's easy with ionic. Ionic, I had a rope out, pulled the rope away, transfer. Who pulls the rope away? The non-metal because it's stronger. Covalent, we show sharing with the rope because the two elements involved have high attraction, high strength, so they're forced to share. Sometimes they share unequally, it's a polar bond. Sometimes right down the middle, non-polar. We've been covering this. Now, what's a metallic bond? I think of the metallic bond as kind of like, think about 4 or 5 families. I'm not sure if this exists. It probably exists back when we lived in villages. Not so much in houses where we're separated. In villages, you didn't really stay in your hut. You kind of went out because the hut was kind of boring. Look at straw all day. Okay, so you went out in the village. Now, when you went out in the village, we lived in villages. They have this saying that a whole village is needed to raise a child. Now, here's how it works. So think about it this way. Since we don't live in a village and we can't really conjure up those images, think about 4 or 5 of your friends, if you have that many, and their families. Let's say they lived in 4 houses that are right next to each other. Okay, so you had 4 or 5 houses of friends. So let's pretend you like your neighbors, and your neighbors had the same age kids as yourself or whatever, and at any one time you can be any one of those 4 houses. So I have 2 or 3 kids, and my kids are over my neighbor's house over here in front of me. And I know that they're good kids. I know the families are good, so I trust them. So I'm never concerned. All right. Now, for me to live in a scenario where my kids are always over 3 other people's houses, and their kids are over my houses, and it always intermingles, we have to inevitably trust the other families that are doing the right thing. And that's hard to do. So if you think about that happening, it's kind of like metallic bonding. The houses represent, or the moms and dads represent the nuclei. They're not going to move over house to house, but different kids are going to be over there. And here's how it works. Is it going to work in this scenario where kids can go house to house to house, right? I could have the neighbor's kids, my kids can be over the neighbors, and we can trust each other to do the right thing, and the kids are behaving. That only works, okay, if the parents aren't over the top controlling, correct? If you had an over the top controlling parents, and I had those, okay, this would not work. What are you doing now? What are you doing tomorrow? What are you doing this minute? Okay, did you take the trash out? What are you doing? Did you practice? Did you do homework? Whoa, chill. In this scenario, it's a little laid back. So where's Johnny? I don't know. He's over someone's house. Where's Billy? Oh, I got Billy here, but he just left. Is he doing all right? I think he's fine. What's up? I don't know. They're doing all right. Okay, where's Johnny boy? Johnny boy, I think he was with Billy, but now Sarah just came over with Rachel, but they just left to go over Slim Jims, and it's, it looks like we have no control. But when we get together as 4 families, do you think they're closer as a group? Yeah, that 4 families are really close. In fact, Even though I may not say like, oh, where's Johnny boy, I'm watching out for what I see. The 4 kids feel comfortable with those 4 families. It's like metallic bonding. Isn't that I don't care, it's just that I'm attracted to the big group. Think with me for a second. I'm a nucleus. I hold on to my electrons loosely. That's why I'm not overbearing. My electrons are free to move from this house to another nucleus and back. I'm a metal. I hold on to electrons loosely. I'm big. So I'm a nucleus, and I am now able to what? Attract all of the kids at once. I'm not going to bend or break. You can heat me, twist me, but because it's essentially metallic bonding is like covalent bonding in all directions. Metals have a lot of electrons. They're loosely held. The nuclei of these metals simultaneously attract all of the electrons in their area. The electrons are free to move throughout everyone's nucleus. If Tony belonged to me, he's my electron. He's free to go to another nucleus because I'm not loosely held. And I'm attracting Tony's electrons as I'm attracting other people's. So if each nucleus is attracting covalently all the electrons that are able to move, would you consider that to be a very strong attraction or bond? And that's why metals, metallic bonds, have the highest melting point. Would it make sense? You can heat me and shape me into a thin wire and it won't break? People that are flexible. The families in these have to be flexible, correct? If I'm flexible, if I'm a person that's flexible, that usually means if stuff happens, you kind of roll it off your sleeve, you find ways to circumvent it. If I'm flexible in this scenario, I'm not going to break. If you twist and bend me, I'm still attracting other people's electrons. But hold my hand. Like we have like a dude shake. Like that. Now this is a covalent bond. Our bond is right here. Right here. You twist or break me, we're going to break. That's why if you drop a dish, it crashes. That's why when I took the racquetball and I soaked it in liquid nitrogen, it was brittle. Metals don't do that. Metals have these bonds in all directions and are able to attract them simultaneously so you can be ductile. You can be malleable. Okay? And you can conduct electricity and heat in any phase. Okay. So that last night was about understanding metallic bonds. Now, what's the formula of something that's a metal and metal? How would you identify something with metallic bonds? Well, what's the chemical formula? If I have copper bonded to copper, bonded to copper, bonded to copper, what will it look like? It would just be copper. You're not going to count. How many copper is in that copper coil? Give me 20 days and I'll count each one. It doesn't work that way. I have pure copper. I just write copper solid. So when I give you chemical formulas, who do you think is metallic bonding? Who is this? Iron, or ferrum if you speak Latin. No one speaks Latin anymore, but that's where it came from. So ferrum is iron. Fe is iron. Table S will tell you. So pure iron is written as Fe, the element iron. It doesn't say I have one atom, I have a bunch of them. This is undergoing what kind of bonding? Metallic bonding. Anytime you see a metal written by itself, it means that metal is bonding with itself. Who knows how many times? Who cares? No one's going to write that number down. No one's going to count. So these guys are undergoing metallic bonding with themselves. I got pure mercury. Mercury. Mercury bonded to mercury. I got pure copper. It's just Cu. Okay? Now, how do I look? And this is the hardest skill now. Assuming you spent time with my lecture and you filled out the back page. How do I take the back page, which discusses the properties of metallic bonding, which is the newest one, with ionic, we talked about it, and covalent. Well, so let's look here. It's the hardest skill. First and foremost, let's look at the first one. Let's find out my ionic ones. Let's give them a color. Let's make them yellow. Ionic, metal, non-metal. Let's go find, Ki. Is that ionic? I've got a metal who holds on to electrons loosely, a non-metal iodine who attracts them. Is there going to be a transfer? Absolutely. Where else is there an ionic compound? I see I see, what the heck is that ion? It's called a nitrate ion. It's -1. This is a metal. It's also ionic. Yes? Any other ionic ones you see? Ionic bonding, ionic compounds. Do I have all of them? You may say, well, what about NH4? It's a cluster this could undergo ionic bonding, but this cluster is actually using covalent bonds to stick together.
What about the one on the water?
NH3.
No, you can't see it.
Oh, it's not there? I'm missing that one? I felt like there's one more too. When I zoom in, I can't see. Oh yeah. Oh yeah, definitely. Good job. Ionic. Can everyone see those three ionic? For two different reasons. Number one, metal, non-metal. Okay? Metal, non-metal, metal, non-metal. This one is metal, non-metals, but still for the same idea. This cluster is negative, this has to be positive. It's sticking together because of ions. You must be able to identify your ionic compounds. These are called binary. Remember how we name them? How do we name them? Name of the metal, potassium. This is iodine, but we add ID, potassium iodide. This is binary too. Metal first, strontium. This is chlorine. Strontium chloride. We did that a couple weeks ago. Now we just learned last week ones that have these clusters called polyatomic. The naming changes a little bit. The ending is the actual name of this cluster, which is given to you in Table E. This is called a nitrate ion. So this is lead nitrate. There's more to that name. We'll get to that. It's good enough for now. All right, so let's look at the choices that talk about ionic compounds. All right, and this is what we have to be able to do. In your next CAT, you're going to have to be able to decipher. I want solid compounds that are found in crystals that conduct electricity. Do ionic compounds conduct electricity in the solid phase?
No.
The answer is no. Excellent. By you saying no emphatically, you're telling me that you clearly understand. Why can't sodium chloride conduct electricity? It's got ions, but they're not what? Well, you're right. They are next to each other. They can't conduct. Why, Kara? Right. They can't move. Excellent. These ions have to be free. And they're free in two ways. You heat them, so they pull apart into a liquid, or they're dissolved by those famous boyfriend, famous girlfriend, aqueous with water. Water can get in between them, compete for charges, and pull these away. So when they're aqueous or liquid only, so this is screaming that this does not conduct as a solid. What solid compounds always conduct? Metals. So where are my two metallic bonds? Who are my two compounds? Fe and Cl. That's how it works. So Fe is a metallic substance. It has metallic bonds. It has that C of what? Mobile electrons that I talked about in the previous lecture. And that was a great visual if you watched that movie. And of course we have chromium. Yes, it was. But it was a great movie. Here's number two. Solid compounds that are found in crystals that do not conduct electricity. Ionic bonds. And there's three of them, so put them down. Yep, we have strontium chloride, Sr, Cl2, and we have lead. You're going to learn this is called lead-2 nitrate, but we'll talk about why. And then Ki. Okay. Number three. Solid compounds that are found in crystals. This could be either metals or ionic substances that will conduct electricity only when melted or dissolved in aqueous solutions. Who must that be? Right. Should that be the same? Didn't we just say that these are ionic? And don't ionic only dissolve, only conduct when they're dissolved or heated as liquids? Yeah, these are the same three. These are making you think about the properties. Not only have to be able to recognize these guys, you have to be able to apply their properties. And they have high melting points because they stick together in that crystal structure.
I have a question.
Yes.
Do you know the difference between like Ki and Kl? You know, like.
Right, I get what you're saying. There's no L though on the periodic table, so that's an I. If you ever have a problem with that, let me know. You're right. That Ki looks like it's an L. I agree. I agree. Okay. Number 4, compounds that have both ionic and covalent. What am I looking for? What am I looking for covalent and ionic? What must I have? What must I have? I must have a cluster of nonmetals acting as a what? Single ion as a cluster, because this cluster has an ionic bond between this metal who's positive, but between the nonmetals there must be sharing. So the answer to this is what? You're looking for something with a polyatomic ion, and it's what? Pb, in this case lead 2 nitrate. Right? Between the ions is ionic, and between the nonmetals is covalent. How much time don't I have today? 2 minutes? 1 minute. Okay. If you have not already done so, I want you to continue and finish this side. Understand this, party people. Okay? Understand this. We figured out who our what? Ionic ones are. We figured out who our metallic ones are. Who are our covalent? The covalent ones are the ones that have non-metal, non-metal. Non-metal, non-metal. Non-metal, non-metal, non-metal. Non-metal, non-metal. Okay, so you should be able to decipher by taking out your ionics and taking out your metallic compounds. You should have left just your nonmetals and follow those. Have a good day.